In section 3.1, you were introduced to groups. And if you recall, a group is a set that has a binary operation. And on that binary operation, there are a number of properties that this set or this group needs to have. For example, the group needs to be closed under that binary operation. The binary operation has to be associative. We know that the group has to have an identity element with respect to that binary operation, and every element in the group has to have an inverse. So those are the four qualities of a group. Then we realize that if the binary operation on a group is commutative, then we know that it is either a commutative group or an abelian group. Today we're going to look at section 3.2, where we talk about properties of group elements. Theorem 3.4 gives us 5 properties that elements in a group must have. And we're going to go through and prove each one of these points. Proposition A says that the identity element E in G is unique. In order for us to prove that an element is unique, we first need to assume that 2 of them exist, and we need to show that those 2 elements have to be equal to each other. So here I'm assuming that X is an element in G, and I'm also assuming that there are 2 elements, E1 and E2 in G, such that X times E1 is equal to E1 times X is equal to E, and X times E2 is equal to E2 times X, and that's equal to X as well. Remember, this is what it means for E1 and E2 to be an identity element. E times X has to be equal to X times E, and that has to be equal to X. So now I'm saying that there are 2 of them that does this. I need to show that these 2 elements, E1, is equal to E2. Since E1 and E2 are identity elements, or that's our assumption here, when I multiply any element times either E1 or E2, I should get back that original element. Well, that applies to E1 and E2. Let's start by looking at the element E1. Now, E1 is equal to E1 times E2. I know this because E2 times any element is going to give me back that element. But I also know that E1 times any element is going to give me back any element. So E1 times E2 also gives me E2. It just depends on which one you decide to choose to use as an identity. But it doesn't matter because you end up with these 2 elements being the same. So we've just proved that E1 is equal to E2. For proposition B, we are to prove that for each element X in G, the inverse, which they denote as X to the negative 1 power, is unique. Again, in order to prove that something is unique, you assume that there are 2 of them, and you show that those 2 are equal. So we are assuming that X is an element in G, X is any element, and we have here 2 elements, X1 inverse and X2 inverse in G. Or X, I'm just using these symbols because I have to be able to identify the difference between the two of them. So I'm calling one x1 and the other one x2. However, when I multiply x1 inverse times x, and I should get e, the identity element. And if I multiply x2 inverse times e in either direction, I will get the identity element. So what I'm saying here, this means that we have two elements that are inverses for this value of x. We need to show that these two values have to be equal to each other. So we know that x1 inverse is equal to the identity element e times x1 inverse. Remember, when I multiply inverses, I'm going to get the identity element. So I can rewrite the identity element as x2, because x2 inverse is an identity element. x2 inverse times x, because that is equal to e, because that's the way I identified it, or I assigned it as an inverse. So I know that that's equal to e times x1 inverse. Well, because this is a group, I know that the elements in a group are associative. So I can regroup this as x2 inverse times x times x1 inverse. Well, guess what that is in parentheses? This right here, according to the way I defined it, that's equal to e. And we know that e times x2 inverse is just going to give me x2 inverse. So I've just shown that x1 inverse is equal to x2 inverse. Hence, the inverse for each element in a group is unique. C states that for each element x in G, the inverse of x is going to give me x for any x in G. So we're going to start off by letting x, or assuming that x is an element in G. Then we know that x is equal to e times x. I can always rewrite e as the multiplication or the product of two inverses. So I know that e is equal to x inverse, the inverse of that, times x inverse. And then I can multiply that times x. This is equal to e because they're inverses of each other. Well, again, like in the previous proof, we know that the associative property holds because we're dealing with a group. And in a group, the binary operation is associative. So I can rewrite this or regroup this as x to the -1 to the -1. So the inverse of x inverse. Well, that's equal to x inverse times x. Well, these are inverses of each other, so we know that that's equal to e. And we know that when we multiply e times any element, we are going to get back that element. So we've just shown that x is equal to x inverse, or the inverse of x inverse. Now we will prove D. For any element x and y, or any elements x and y in G, we need to show that the inverse of xy is equal to y inverse times x inverse. Okay, so we just learned that the inverse is unique. The inverse of any element is unique. We learned that when we proved B. What this means is if xy inverse is equal to y inverse, if that is true, let's just assume it's true for now, then that means when I multiply xy on both sides, I know I have to get the identity element, because these are inverses, and if these two are equal to each other, then, and we know that the inverse is unique, then I know that this has to be the inverse of this, and so this should also give me E. So what we're going to do is we're going to see if we can prove that that's true. If I want to show that the inverse of xy is equal to y inverse x inverse, I need to show that y inverse x inverse is times xy is equal to E, and I also need to show that xy times y inverse x inverse is equal to E. So that's what we will do. So we have y inverse times x inverse. When I multiply that times xy, let's look and see what we can do with this. It's a group. The operation in a group is associative, so I can regroup this as y inverse times x inverse times x times y. But what's in the middle is just E. Y inverse times E times y. Well, what is y inverse times E? Y inverse times E just gives you y inverse, and I'm left with times y, and we know that this gives us E. Also, if I were to do this, if I were to move it around or commute the factors, I end up having xy times y inverse times x inverse, and we want to show that that's equal to E. It's a similar proof. X times y inverse times x inverse, because it's associative and I can group elements differently. This is x times E times x inverse. Well, I know that x times E is x, and I'm left with times x inverse, which gives me E. So I've just shown that y inverse times x inverse is the inverse of xy. In other words, I've shown that these two have to be equal. To prove E, we will let A, x, and y be elements of G, and we're going to assume that AX is equal to AY. Well, if AX is equal to AY, then if I were to multiply, let's see, AX is equal to AY, that implies that A to the inverse times AX is equal to A inverse times AY. Well, that implies, because it's associative, I know I can regroup this, and we end up with this, of course, we know is E times X, and this is E times Y. We end up with X equal to Y. We would have to prove the other one as well, but it's a similar proof. Here we have proven these 5 points